I think we should really move on to the next talk, which was again partially advertised. It will be now about the 2+1-dimensional Gross-Neveu model. And the next talk will be shared by two speakers, Mark Wagner and Lennart Kurth. And I think Lennart is going to start, if I'm correct.
Yes, so let me share my slides. Can you see them?
Yes.
Okay, then let's start. Thanks for the organizers for the opportunity and welcome to everybody listening. So we just talked about the 1+1-dimensional Gross-Neveu model at finite flavors and also partly already about the 2+1-dimensional Gross-Neveu model, which we will here consider only in infinitely many flavors. And the talk is shared. And my part one will be about a continuum approach. Later, Mark Wagner will tell you about a lattice approach. Okay, good. Well, the motivation is always similar. We would like to know the QCD phase diagram, but it's too difficult. So what we do is we consider simplified models. In this case, the Gross-Neveu model, which has next to no resemblance of QFT apart from this discrete chiral symmetry. But anyway, we want to know, we want to learn something about inhomogeneous phases. And we further consider lower dimensions because QFT is easier in lower dimensions. And well, the Gross-Neveu model originally is in 1+1 dimensions and has been investigated by Thies and collaborators a long time ago, and they already found inhomogeneous phases there. So this is the motivation to look for them further in the Gross-Neveu model. In 2+1 dimensions, there have been like homogeneous studies by Klimenko. And then is the question, what is about inhomogeneous phases? And there have been two recent works with different results. So both are lattice investigations, but some find inhomogeneous phases and some don't. So know what is right, or better, under which conditions are the inhomogeneous phases favored. And as I already said, so this continuum approach is indeed a stability analysis, which Stefano in the beginning explained. And on the lattice, we can, on the other hand, do a full global minimization and find inhomogeneous phases, even if they are not connected by a second order phase transition. Okay, Gross-Neveu model in 2+1 dimension, just very short. We have NF quarks, and also the coupling has mass dimension -1, which would hint to non-renormalizability. The model is indeed non-perturbatively renormalizable, and which is nice because in higher dimensions we do not have this feature anymore. And another thing which we have to take care of is the fermions. And in 2+1 dimensions, it's because it's an odd dimension, it's a little bit more difficult. There are two different irreducible representations which have dimension 2, but those have no analog of gamma 5 and therefore no chiral symmetry. And what one can do is one can combine these two to construct a 4-dimensional representation, which then has this discrete chiral symmetry, which we want to have for interpretation. But in the end, it turns out that if we only allow for space-dependent condensates, that it does not matter which Dirac representation we use. It's 2 or 4-dimensional. Well, then the usual procedure, mean field approximation here just means large NF. So at first, we want to get rid of the quartic fermion coupling and therefore bosonize the model. And afterwards, we can integrate out the fermions, which gives us this path integral here with this effective action, which we now want to minimize with respect to sigma. Of course, there is this simple part sigma and the difficult part from the fermions, which diverges. So, and here we have also the model is renormalizable. We have to choose a regularization scheme, and we use the Pauli-Villard scheme. As has already also been pointed out, it's better to use a Lorentz invariant regularization scheme if we want to look for inhomogeneous phases. And this is the case here. Under this scheme, the effective action itself is indeed not is not finite, but differences for different masses. so it's sufficient for our purposes. And furthermore, we only apply this regularization to the divergent vacuum part, not to the medium part, but it's only technicality. The qualitative results don't change. And in the end, as also said in the last work, in the last talk, I mean, we express everything in units of the vacuum expectation value, sigma naught. And this is possible because there is, apart from our cutoff scale lambda, the only mass scale. And for this regularization, we can, for example, express our coupling constant by this relation. Okay, then the reminder of a homogeneous phase diagram. The black curve is the renormalized result, which again has been known for a long time. And the other curves here are now for finite regulator. And there we see that now there's a first order phase transition, the solid line here, which was not there before in the renormalized limit, where only at t equals 0 there's a first order transition. The region in between the dotted lines is just the spinodal regions where there are two minima, but the physically important parts are the first order lines here with tricatrical point here, and second order phase transition, well, because we consider the massless Gross-Neveu model. And this homogeneous phase diagram we need later for searching for inhomogeneous phases, because we work with a stability analysis. So the problem is, okay, we would like to minimize this determinant term here. And to minimize it, we have to take the derivative and have to set it 0. That way we find the minima. But if we take the derivative of the logarithm here, we get the inverse operator. And we can only invert this operator for either specific ansatzes, as we already heard, or for constant mass. And what we do here, we expand these terms around the constant sigma, and then look at the first and second derivative to find instabilities. Okay, the global minimum we have already identified on the last slide, and we find that if we now expand around this homogeneous minimum, the global homogeneous minimum, then all first derivatives vanish. If we just expand around any homogeneous minimum, then around any homogeneous point, there might be a finite derivative in the homogeneous direction, but in all other directions, it's 0 anyway. So what we have to do is we have to go to higher derivatives. And well, to the second derivative, we get this Hesse matrix. And if we now want to know if there's some direction in field space in which we can, so to say, move our expectation value such that the effective action gets smaller, then we have to determine the eigenvalues. So we diagonalize this operator. Since we expand around the constant sigma, this can always be done by a Fourier transformation. So the second derivative of the effective action is diagonal in momentum space. And on this slide here, it's just that, so you have something to imagine, well, what does this inverse propagator equals a second derivative looks like. It's plotted against the momentum. Well, we expanded around the homogeneous minimum, so we already know that here at q equals 0, gamma to the minus gamma inverse must be positive, and we find an instability if for some momentum these lines go below 0. So, for example, here I go through some values of the chemical potential, and for the blue curve there is no instability. The orange curve just touches the 0. So this might be the beginning of an inhomogeneous phase. And the green line has this instability for these momenta. So what we at this point can say is that there is some field configuration that is favored, which is inhomogeneous. We don't know what it is. We just know that it exists. On the other hand, for example, at a chemical potential temperature for the blue curve, we have no instability, but we cannot exclude the possibility that there is an inhomogeneous phase. But this is all the stability analysis can do. And if you want to know more, you have to do ansatzes or lattice studies. Okay, and then we come already to the result. This is how it looks like, what we find. we find no inhomogeneous phases for lambda to infinity, so in the renormalized limit. But at finite lambda, we find inhomogeneous phases, and they look like this. And now is the question, can we see this even somehow analytically? So here's a Lifshitz point, here's a Lifshitz point, but does it really go to 0, or how is the behavior exactly? And the nice thing in 2+1 dimensions is that we can calculate many things analytically. Here is this homogeneous result, but not only the phase boundary, but the complete non-vanishing expectation value can be given analytically. The second order phase boundary can be given analytically also for finite regulator. Unfortunately, not the first order one. And the Gross-Neveu model in 2+1 dimensions is one of those simple models in which the Lifshitz point always coincides with the tri-critical point, which again hints at no inhomogeneous phases in the renormalized limit. And perhaps the best result here is that we can give the Lifshitz point analytically expressed through this Lambert wave function. And this is my last plot on this matter. Here you see how the tri-critical point equals Lifshitz point moves if you increase the regulator. Of course, this is also everything is regulator scheme dependent, but the qualitative results remain the same. And you see here you have to go to very large cutoffs and to get close to t equals 0. And with this, I want to conclude the first part of the talk. So we find no inhomogeneous phases in a renormalized model, but we do as soon as we have some cutoff. And with this, I want to let Mark speak about the lattice results.